right, guys, today we are doing actually our final target for Unit 8, Target 5. I can graph a system of inequalities and identify possible solutions. So far we've done systems of equations. Now we're doing inequalities. And this really is a nice review of things we've done before. We have graphed inequalities before. We just haven't graphed systems of inequalities before. So to start off, we're going to do a quick review of how to graph an inequality. First one is a linear inequality. These we did first semester. So if this is in like a standard form of a line, I'm going to subtract my x and put it into slope-intercept form. Now the reason I picked this one in particular is because here we have to divide everything by -2. If we divide by a negative number, notice your inequality symbol has to flip. So I can graph it. I can start up here at +1, and I have a 1/2 slope, so up 1 and over 2, or down and to the left. Now, the other thing we have to figure out or decide when we are graphing these is it a solid line or a dashed line? Now, we look back at the inequality symbol, either inequality symbol here, because it does not have the equal to part onto it, we know it can't actually equal any of the ordered pairs that are on this line. So that means we show that, if you remember, by drawing it with a dashed line. Now we have to decide where to shade it. We had a couple different ways to decide how to shade it. So to shade it, we can either test a point or just look at above or below the line. If we were to test a point, if you remember, a nice easy point to test was the point 0, 0. Do you have to pick 0, 0? No, it just makes it nice and easy. If I plug in 0, 0, I do 0 minus 2 times 0, I could put it into this one, is less than -2. So is 0 less than -2? No, it's not. If you plugged it into this inequality and slope-intercept form, you'd get 0 is greater than 1/2 times 0 plus 1, or 1. Is 0 bigger than 1? No. So you should get no for either of them. It doesn't matter which one you do. That means we are not shading the side with 0, 0 on it. We want to shade the opposite side. Now, if you were to think, instead of testing a point just above or below, you have to always go back and look at the equation that has the y by itself. That's super important because we want all the y values. That means I'm looking on my y-axis. We want all the y values that are bigger than this right-hand side with the x. So that means I can pick any point really along this line. I like to a lot of times pick the y-intercept and think, all right, if I'm at the y-intercept of 1, I want every number that's bigger than that. All the y's that are bigger than 1 are up above it here. So we are shading everything up above. So that means we are shading all up here. And this is our solution set. Now, if you remember before when we did these, I usually asked you for some possible solutions. Now, these are just examples. How many possible solutions are there? Hopefully you answer, there's an infinite number of solutions. Now, infinite doesn't mean that every single ordered pair works in this inequality. It just means that there are an infinite number of them, that they keep going on and on and on and on and on. So we pick some. Let's pick, I don't know, 0, 3 is a nice ordered pair that would work in there. That's on in the shaded region. You could pick 1, I don't know, up here at 5. I could pick some negatives. If I pick -6, this is obviously going to go really big. You could go even bigger, but I'll go to like 10 or so. And those are some ordered pairs that would work. Again, there's an infinite number. This is just an example to kind of remind ourselves that that is where our solution set is. All right, what we haven't done so far is graph inequalities with parabolas. But you'll notice they're actually very, very similar here. We're going to graph our parabola first. So this one's in vertex form, nice and easy. We go to the right 3 and down 1, 2, 3, 4, 5, 6. That's our vertex. No stretches or compressions here, so I'm going to go up 1, then go back to your vertex, and then we count to the right 2 and up 4. Because 2 squared is 4, then 3 squared is 9. And we have our points here that we can look at. Now, we still have to look at solid versus dashed. There are dashed parabolas. I know it seems maybe a little bit weird, but there are dashed parabolas. That just means that it's the border part of it. This one, however, is not a dashed parabola because it has the equal to on it. It is a solid parabola. Now, when I graphed the linear inequality, you could kind of easily see that it splits your graph into two sides of the, on your graph paper there. Not necessarily equal on the graph paper, but two separate sides of the graphs. It actually does the same thing with the parabola. It may not look like it right away, but again, this parabola keeps extending and going on and on and on and up and up and up. So really what there is there's an inside part to the parabola and an outside part to the parabola. So we have to decide which we're going to shade. And it all has to do with the inequality symbol. So again, this one is we want all the y's greater than. So you can really pick any point along the parabola. Just for simplicity's sake, I like to a lot of times pick the vertex because it's nice and easy to see. We want all the y values bigger. So once again, we're doing above it or below it. So if we want numbers that are bigger numbers are going to be up above. Again, you could actually pick any point on the parabola. All of these are going to be above it right here. That means greater than this particular parabola is going to be inside the parabola. Now be careful, greater than is not always inside. Some people like to try and just memorize that. It is not necessarily always inside. It depends if your parabola is concave up or concave down throughout its entire domain there. So this one happens to be greater than would be our inside part. So now we want to pick three solutions. Again, we can pick anything. One thing that's kind of unique about this here is I can actually pick any solution at this time on our parabola. So reasonably, I could pick the ordered pair 0, 3 because it is on our parabola. This one is a solid parabola, so I could pick anything on it or inside. So inside the parabola, I could pick 3, 0 as well, or I could pick, I don't know, 4, 3. Again, these are just examples. Now, the idea behind a system is we want to know which ordered pairs work for both of them. Now, if you graph them on two separate graphs like this, it's kind of hard to tell, right? So that's a little silly to use two separate graphs. So instead, usually what we do is we put them together. Now, I wanted to do them separately to make sure we could graph an inequality parabola and then also remember how to graph a linear inequality as well. But let's see if we can figure out which ones would be solutions to both. Now, you'll notice I happen to pick 0, 3 for both of them. So 0, 3 is a solution that works in both. Now we can pick other ones. If I picked 3, 0, no, that doesn't work in my linear inequality. But what about like 3, 5? Would 3, 5 work? I think so. And 1, 5, actually, I picked for my linear one. That also works for my quadratic. Again, these are just examples here. All right, let's put these together then. So let's start with a somewhat easier linear inequality here. If I graph, these are just horizontal and vertical lines. If it's x is less than or equal to 4, we know that one is a vertical line. It's also a solid line, so it's a solid vertical line going through 4. We want all the values that are less than that. Less than that vertical line, again, vertical lines are the only time you're ever going to go left and right because now we're looking at, I'm in highlighter, but now we're looking at the x-axis right here. So if we want x's that are smaller than 4, that's going to be everything over here to the left. Now you'll notice I'm using highlighter as I'm doing it just because on a computer it's kind of hard to show how to graph, with a pencil and graph it light. So what I encourage you to do is just graph it nice and light. I also tend to go in the same direction as the line. So this is a vertical line. I would do kind of nice and light ones in a vertical strokes right there. So that's something that I would usually look at. All right, y is greater than -5. So we're going to do a dashed line, and it's going to go through our y-axis at -5 here. Dashed line going through here. We want all the y's bigger. So y's that are bigger are going to be above it. Again, you can still test 0, 0, 0 is bigger than -5, so 0, 0 is a solution up here. And then we're going to shade everything else above it. You'll notice I'm shading all of it, even parts that aren't for the other line. I'm just kind of ignoring the other line here and shading everything above that horizontal line. Now, we want to know really where these intersect. Again, if you did it using pencil, you can use different colors if you want to, or you can just shade lightly. And again, I like to kind of go in the direction of the line so that way you can kind of tell where they overlap. Because not everything that's shaded here is a solution. Really, it's just the part where they intersect. So what I'd want you to do is actually shade that a little bit darker. If you want to, you can also erase the other parts that you have graphed, like this other light pink part and the other light blue part. You can actually erase those. I don't need you to. Really, I just encourage you to shade that darker. And that is where our solutions are. Okay, so we can pick three possible solutions. This is to just make sure we know what we're doing here. So 0, 0 is a solution. I could pick 1, 1, and I could pick -3, -3. I'm just picking up some random ones there. Let's try another one here. All right, there's another two linear system of inequalities here. Both of them are linear. First one goes through 0, 0. Be careful on that. Has a slope of 3. We also notice that this one is going to be a dashed line. Now, I like to shade right away. Do you have to shade right away? No, you can save it to the end. I like to shade right away, otherwise I start to get a little confused on which line is which. But you can save the shading until the end. We want all the y's that are less than that. Again, you can pick a point. This time you can't pick 0, 0, remember, because our line goes through 0, 0. Instead of picking a point, I'm going to go a little quicker. We want all the y's less than. That means we want everything below. So I'm going to shade everything smaller than that line in this direction here. It's our less than. All right, let's grade or graph our other one here. So I'm going to start up at +1. Oh, I'm still on inequalities here. Hold on. I'm going to start up at +1 and -2 slope. Same in the other direction. This one is solid. And again, we want to think about where we are going to shade it. So I am going to shade everything greater than this y value. If you wanted to plug in 0, 0, you'd get 0 is bigger than 1, which is not true. So we're shading the other side. Or again, pick a point and think, okay, it's greater than, we're shading above it. So that means everything here. And now we can tell where our solution is. Again, I'm going to make that a little bit darker. This region over here ends up being our final solution part. Shade that part a little bit darker. You know what, I'll even use black here to make it obvious. That is where our solution set is. So pick some points. We can even go easy. I'll do 3, 0, 4, 0, and 5, 0. All right, try the next couple. Both of these are linear. I'm going to pause my video and fill in my answers and try them and see how you do. All right, I'm back with these two linear inequality systems. Looking at the first one, again, just be really careful when you are solving for y that you flipped the sign because you divided by -3. I shaded all of my regions. It was greater than y is greater, so it was greater than -x on there, so it was shaded above the blue line. Then it was less than 2/3 x plus 3, so I shaded below the pink line. And then we can see I shaded in darker the other region. Now, number 4, I took a different approach. I didn't shade them individually. I kind of thought in my head a little bit more about where those solutions might actually end up. So if you look at it, I graphed both of them. Take care on this first one that, again, the inequality symbol did flip. So it's less than 2x plus 5. So it was below our first line. Then the second one, I did not flip the sign because I just divided by a +2. But it was also below that line. Since it was underneath both, it ended up being in this bottom region here. All right, so let's try a couple more together. And again, I'll have you try some on your own as well. So looking at number 5 here, this one is a linear and a quadratic together. So I start up at 2 and I have a slope of 1. I like to fill them all in to make my graph look nice and neat here. And we have it as a dashed line. So again, if I'm going to shade this right away, Less than is going to be below that line right there. So I'm going to shade everything underneath that line. Now we have a quadratic. Again, we haven't done a lot with quadratic inequalities, but they should be pretty similar. So if I'm graphing the other one, I'm going to start down here at -4. Oops, sorry, hold on. Let me get back to the pen. Start down here at -4. Has a no stretches or compressions here, so I'm going to go up 1, go up 4, and go up 9. Notice this one is another solid parabola. So I'm going to graph it solid here. Now, this is y is greater than or equal to that parabola. So again, I always kind of go to the vertex point on here. If I go to the vertex and think, all right, we want all the y's that are bigger than where this vertex is. That means we're going to shade above it right here. Above it on this parabola is inside. So I'm going to shade everything inside this parabola. So that means we can tell now where our shaded region or intersection of shaded regions ends up being. It's going to be everything inside. Now, is it always going to be that little space inside? Absolutely not. Sometimes it is, sometimes it is not. So you just want to be careful on there. Sometimes when you have a small space like this, you have less points to pick, but keep in mind there's still an infinite number of points to pick. I mean less integer points to pick here. So 0, 0 is a nice easy solution. You have a lot of nice points here, but don't forget fractions are also a part of this. So you could choose like 1/2 0. You could choose 0, -1.5, etc. You can do fractions in there. So just because there aren't a lot of nice integers to pick does not mean that there aren't enough points to pick. There's still an infinite number of points in there if you include all the fractions, decimals, and everything like that. All right, let's do another one here together. So I'm going to start with our line 2x plus 3. We know then this one is also a solid line. I'm going to save the shading on the end to this one here. So I'm going to do the 2x plus 3. Let me do a different color for the parabola though. We're going to start at 0, 0. This one is just our parent function. Everything up here. And notice this is a dashed parabola. Move this up here. I'm actually even going to extend this line a little bit further just so we can see that where they do actually cross up there. Okay, so let's think through this one. We want less than the line and less than the parabola. So less than the line, let me shade all of that part first. I'll shade that in, we'll go in blue. So less than the line is going to be everything over here. Okay, below that line. And then less than the parabola this time. Again, less than the parabola. I go to my vertex and I think we want smaller. That means down here. So less than the parabola is actually everything outside that parabola here. So it's everything outside the parabola on this one. That is a less than here. Now, in this particular one, again, we want to decide where are they intersecting. So this one is not intersecting on that inside little space here. This one is intersecting underneath the parabola and under the line. So everything all in this darker region that I'm shading here. Kind of a weird shaded region. Again, it keeps going on and on and on forever in all the directions. But that is going to be our solution set. Everything up over here. Again, under the parabola, under the line, just to make it look a little bit darker there. So again, you can pick some solutions on your own. Go through again. You could do 0, -1, 0, -2, 0, -3. You can pick some easy solutions as well. Again, I'm going to pause it and start graphing these so that way the video isn't too long, but then you can kind of go back and check your work. All right, just to kind of talk through these, you'll notice that some of them are in standard form for a parabola. So hopefully we remember doing this in our previous units here. Again, that's one of the big things with an A-level class that you have to make sure you still remember the stuff that we learned before. So I did completing the square. I subtracted the 3, then get x squared plus 6x. We have to add 9 to both sides of the equation. And the whole point of doing that is now this trinomial is a perfect square trinomial, so it factors to x plus 3, the quantity squared. Subtract the 6 back over, and we have our vertex form to graph. You'll notice that it's less than both of these parabolas here. So it's shaded underneath both of them. Again, I'm going to, and just for simplicity's sake on a computer, just shade our final region. You can do that too if you can handle that. Otherwise, I like when you shade everything lightly and then just shade the intersection a little bit darker. All right, looking at the next one, you'll notice that we have one in factored form. Again, this was also called intercept form because it gave us our y-intercept, or I'm sorry, our x-intercept, my goodness. So we have a x-intercept at 2 and an x-intercept at 6. So those are also known as our zeros. So we know then our vertex has to be halfway between, and it's going to be just down 4. Once again, it's actually less than both of these, so it's everything shaded underneath both. Looking at the next one, we have another completing the square. This time we have to factor that 2 out. So I moved the 5 over, and then you'll notice I factored the 2 out to leave us with x squared minus 4x. So we're adding still half of 4 squared. So I'm adding 4 to the inside of the parentheses here. But remember, really, that means I'm adding 2 times 4, or 8 to the other side. Now I can factor that trinomial to x minus 2 squared. Move the 3 back over, and we have our our vertex form here. So this one is less than our vertical line. So to the left of the vertical line, that's the blue line, and then greater than, that means bigger than the parabola or inside it here. Last one here, you'll notice we have one vertex form and one standard form. Remember, when it has a negative out in front, you still have to factor that out. So I moved the 10 over. When you factor the negative out, notice that gives you x squared plus 8x. Half of 8 is 4. 4 squared is 16. But really what you're doing, you're not just adding 16, you're actually adding negative 16. So subtract 16 from that other side there, and then we factor it and get our vertex form. So again, when you're looking at this, it is greater than the one that has the compression of 1/2, less than the one that is reflected here. That means it's going to be in that little region inside. All right, try these on your own, see how you do, and let me know if there's questions.